Today in the workshop, we're taking a first look at the new Arduino GIGA. We'll learn about the unique features of this microcontroller, including its 16-bit A to D converters, USB-A connector, and real-time clock. We'll also build a waveform generator using the GIGA's 12-bit digital to analog converters. It's the most powerful Arduino yet, so welcome to the workshop. Well, hello and welcome to the workshop, and today we're going to be working with a brand new microcontroller board, the Arduino GIGA. Now, the Arduino GIGA is a large board that has the same form factor as the Arduino Mega 2560 and the Arduino Do, and it also has compatible pinouts, but that is where the resemblance ends. This is a board that doesn't have its heritage in the Arduino AVR line of microcontrollers. Instead, this board hails from the Arduino Pro line, and it uses the same processor that the Arduino Portenta uses. Arduino is calling this the most powerful Arduino board ever created, and it certainly is a monster. It has more I/O ports than the Arduino Mega, a total of 76 of them. It has 16-bit analog to digital converters, 12-bit digital to analog converters. It has an integrated real-time clock, and one of my favorite features is it has a USB-A connector that you can connect external USB storage devices to. You can connect keyboards or mice to it, and you can use them within your Arduino programs. It has a very powerful microcontroller, probably the most powerful one we've ever seen in the workshop here. It runs circles around things like the RP2040 or the ESP32. It, of course, has Wi-Fi and Bluetooth as well. Now, this board has so many features that even though this video is an hour long, it would be impossible for me to cover all of them, and there's no reason to really cover a lot of the standard features. We all know how to blink LEDs, drive motors, and read sensors. So instead today, what I'm going to do is I'm going to focus on some of the more unique aspects of the Arduino GIGA, and we're going to start off by learning a bit more about this amazing microcontroller. The GIGA is based around an STM32H7 processor, and it includes both Wi-Fi and Bluetooth. This large microcontroller board has a whopping 76 digital I/O pins, and 12 of those pins are capable of pulse width modulation. It also has 14 analog inputs, and it has a 16-bit analog to digital converter. In addition, there are 2 analog outputs in the form of 2 12-bit DACs. The onboard memory includes RAM, flash, and SD-RAM. The GIGA has an integrated real-time clock. There are USB-C, USB 2.0, and a 3.5mm audio connector on the board. There are also connectors for a display and a camera. This microcontroller has a number of different applications. One obvious one is robotics, where all of the I/O ports and the power of the dual-core processor will really come to advantage. Since it has the same form factor as the Arduino Mega, it's a natural for 3D printing. This board could be used to update and improve 3D printers to allow Wi-Fi and Bluetooth connectivity. Since the GIGA can be used on the Arduino IoT Cloud, it's a natural board for IoT projects. Its 16-bit digital to analog converters would allow it to be used for audio processing and analyzing applications. And of course, this is pretty well the ultimate board for makers and hobbyists. The GIGA has the same form factor as the Arduino Mega, and it has the same pinouts as well. For this reason, you can use accessories designed for both the Mega and the Uno when prototyping with the GIGA. If you want to use some of your Arduino shields, though, be very careful because the GIGA is a 3.3 volt board and is not 5 volt tolerant. Now let's take a look at some of the connectors on the GIGA board. There's a USB-C connector, a USB 2.0 connector, a 3.5mm audio connector that is both for input and output. There's a micro UFL connector for an antenna. There is the same collection of I/O ports that was available on the Arduino Mega. And just like the Mega, there are a group of analog to digital converter inputs as well. There are a number of power and reset pins, and we'll take a closer look at a few of them in a few moments. There are connections for UARTs, 3 connections for I2C, 2 DAC outputs, and a CANBUS connection, or at least the logic signals for a CANBUS connection. You'll still need a transceiver to connect to a CANBUS. There's another connector which has additional I/O ports and can also be used for a DSI display. A second connector can be used for more I/O ports or for an ArduCam compatible camera. The Giga has the same SPI connection that the Arduino Mega had. It also has a JTAG connector so you can perform debugging operations. And there are 2 switches on the Giga, a reset button and another one labeled Boot 0, which we'll discuss in a few moments. The Giga is based around the same processor used in a lot of high-end Arduino products, the STM32H7. This is a dual-core processor. The first core is a 32-bit ARM Cortex-M7 that has a dual-precision floating point unit and runs at a whopping 480 MHz. The second core is a 32-bit ARM Cortex-M4, and it also has a floating point unit and operates at 240 MHz. Both of the cores can run independently, and it is even possible to run a MicroPython program on one core while you run an Arduino C++ program on the other core. This has amazing applications, for example in robotics where you could use the C++ code to handle the sensors and the motor driving, while you use the other core with a MicroPython program to do the navigation logic. Wi-Fi and Bluetooth capabilities are provided by a Murata 1DX module. The Giga has Wi-Fi capabilities up to 65 megabits per second. It also supports Bluetooth Low Energy version 5. You should note, however, that with the current version of the Arduino IDE, you'll only be able to use version 4. There are several sources of memory on the Giga board. The STM32H7 chip itself has 2 megabytes of internal flash and 1 megabyte of RAM. There is also an additional chip with 16 megabytes of flash, and another one with 8 megabytes of SD RAM. The Giga has several communications options. There are 4 UARTs, 3 I2C connections, 2 SPI or serial peripheral interface connections, and a CANBUS connection. The Giga also has an ATE CC608A chip for security and encryption purposes. Now let's take a closer look at a few of the connectors on the Arduino Giga. The USB-C connector can be used to provide power for the Giga. It requires 5 volts in this configuration. It can also be used to communicate with the computer so that we can program the device and use the serial monitor. The Giga can also be used as a USB peripheral, and that includes sharing out some of its memory that will appear as a thumb drive to a computer attached to it. The Giga can also be used to emulate a mouse, keyboard, or other HID or human interface device such as a game controller. The USB 2.0 connector is a Type A connector and is used for connecting external devices such as thumb drives or SSDs. There are 3 pins on the side of the Giga labeled off, ground, and VRTC. The off pin can be used as a power switch. If this pin is set to ground, the Giga will turn itself off. The VRTC pin can be used to supply power to the real-time clock in the Giga. This can be used to keep the real-time clock active even when there is no other power applied to the board. In addition to taking power from the USB-C connector, you can also use the V-in pin, and the Giga has an internal buck converter that will regulate its voltage. You can apply from 6 to 24 volts DC to the V-in pin. There are 2 buttons on the Giga. The first one is labeled Boot 0. This button can be used to perform a firmware update on the board. You can also use this button in your own code and read its status. There's the typical onboard LED common to all Arduino boards, and it also can be used as a status indicator for the Mbed OS. There's a reset button, which of course resets the board, and is also used in the reload process for the firmware. The Giga has a 3.5mm tip ring sleeve jack. This provides outputs for both DAC 0 and DAC 1. It also is connected directly to analog input A7, so you could use a microphone. These connections are also available elsewhere on the board. There's also a connection for an antenna for Wi-Fi and BLE, and an antenna is included when you purchase the Giga. Further down the board, we'll see a camera interface. This is a 20-pin interface compatible with Arducam cameras. If you're not using a camera, you can also use these extra I/O pins for your application. And on the other side of the board, there's an interface for a display that uses the Display Serial Interface Standard, or DSI. This is a 24-pin connector that again can also be used as additional I/O ports. And so now that we've seen all the connections on the Giga, let's take one out and start working with it. And here it is, my new Arduino Giga, and this is exactly how I received it in the box, mounted on a plastic frame, which is kind of a nice thing to have for prototyping. And of course, you can take it off the frame when you want to use the Giga in its actual application. Now, as you can see, it's a very nicely made board. Here are all the connectors on the side, the USB-C, the other USB jack that can be used for like an SSD or a memory stick or something. And this is an audio connector. Don't confuse that with the power connector on the older Arduino Mega. And as you can see, pretty well the same layout as the Arduino Mega as well. Now, I've got a few other things here in the workbench with me, including the remainder of the packaging, the box, the stickers that come with it, and the little antenna that they have. And the antenna, this hooks over here. There's a little UFL connection over there for it. And of course, you could use another antenna if you had a compatible connector. Now, I've also got an Arduino Mega, or at least a Mega clone over here, and we can put the two of these together and sort of see. You can see indeed they are the same form factor and, the same pinouts on these connectors anyway. Obviously, the Mega is missing a few of the connectors that they have on the Giga over here. Again, though, just be careful if you're going to put cards onto this, such as shields that you have for the Mega, because this is a 3.3 volt device. Now, the other thing I have over here are a couple of prototyping shields that were made for the Mega, and these will actually fit onto the Giga as well. So if you're just doing some prototyping and you want to do some simple solderless breadboarding with it, you can still make use of all the stuff that you had for the Arduino Mega, and for that matter for the Arduino Uno if you're only interested in the pins down on this level over here. So there you go, the brand new Arduino Giga. Now let's start working with it. Okay, I've just booted up my brand new Arduino Giga, and as you can see, the built-in LED is cycling through red, green, and blue, and this is actually normal for a brand new Giga. It just means it's a healthy board. Now, this LED can also be used as a status indicator for the state of the mbed OS, and that's the operating system that holds the Arduino code. And if it is flashing rapidly 4 times, followed by flashing slowly 4 times and repeating that cycle, that means that there's a problem with the mbed OS, and there are instructions on the Arduino website for fixing that. But now that it seems that I have a healthy board, let's go and write some code for it and watch it work. Now, as I said at the beginning of the video, this is a brand new microcontroller from Arduino, and a lot of the software for this microcontroller is still in a development phase. There are examples that Arduino provides in their excellent documentation. However, some of the code samples are taken from the Portenta and don't quite work correctly with the Arduino Giga. Now, I'm going to go through a number of code samples with you today. A few of them I had to correct, and you can get the correct version on the article that accompanies this video on the DroneBotWorkshop.com website. You can download them all over there. But more importantly, I want you to realize that this is in its infancy and this stuff is going to improve, so don't judge the board on that. I even had some difficulty setting the board up using Linux, although it's set up correctly with Windows. And so let me show you how I set up the board and how I resolved that Linux issue. We'll run some example sketches, and then we can start working with our new Arduino Giga. Now, before we start using our Giga with the Arduino IDE, we're going to need to install the board using the Boards Manager. Now, I'm showing you IDE version 2, but you could also be using IDE version 1.8. It will work with either one, but you do need to have a recent copy of the Boards Manager because the Giga board has only been added to the Boards Manager recently. So just open up your Boards Manager, and all you do is you simply type in Giga. And there it is, the only entry, the Arduino Embed OS Giga boards by Arduino. And we just hit install for that. And that's all there is to it. Our board has now been installed in our Boards Manager. Now, I'm sure a lot of you are looking at the screen right now and thinking, is he really going to demonstrate this using the Blink sketch when this microcontroller is so powerful? But that's not why I have Blink up right now. What I want to illustrate is that under Linux, I've got a bit of a problem using the Arduino GIGA R1. And I want to show you what the problem is, and then I'll show you how to repair the problem. So I'm going to upload Blink. I've got my Giga connected, and it compiles as you expect it would. It goes to upload. And here's our problem. And first of all, if you look at the board itself, you can see that the LED, the onboard LED, is actually just kind of pulsing green. That's not the blink that I asked for. It never uploaded anything. And it's complaining about a DFU suffix signature. DFU is the device firmware update. And by the way, that pulsing green means that this is in firmware update mode, but it just hasn't completed it. It wasn't able to do it because of this error message. Now, I thought this might be a problem with this machine or with the 2.0 version of the Arduino IDE, so I tried it with the same machine with the 1.8 version of the IDE. I got the same problem. I tried it on a few other Linux machines, all of them Ubuntu Linux, mind you, but the last two versions of Ubuntu, and I still had the same problem. And then I moved over to some Windows machines, and I'm able to upload it in Windows. I can upload it in Windows 10 and in Windows 11, and in both of them I get a warning about this, but it goes and proceeds. And so I thought, well, I could do the demo in Windows, but I really do want to fix this in Linux. And so I've done a little bit of research, and I think I figured a way to fix it out, and I want to show you that right now. Now, when I first received my error, one of my first impulses was to go to the Arduino forum, because I figured if I'm getting this on every one of my Linux machines, chances are there are other people who are as well. And in the Arduino forum, in the hardware section, they've got a section just for the GIGA R1. And sure enough, the very first topic, or at least right now in the forum, is cannot blink at first attempt on GIGA board. And this is exactly the problem I'm having. I'll go to the top of the thread here for you, and you can see that this is the problem that we're getting, the same one we have. Now, interestingly enough, there are people on this thread who also claim they're having a similar problem with Linux, with Windows. And I didn't have that problem with Windows. I tried it on two Windows 11 machines and a Windows 10 machine. It worked fine. But if you do have a problem, this is the thread to head to. And I'll leave a link to this thread in the article that accompanies the video. Now, with the information here, I was able to fix one of my other Linux machines, and I created a cheat sheet of commands you can use with Linux to do that. You can also get the cheat sheet on the DroneBotWorkshop.com website in the article accompanying the video. And here's how the cheat sheet works. It's a text file over here. I'll show it to you big for a second so you can see. So basically, we need to close the Arduino IDE. We need to open the file manager and navigate to this and open a terminal, or you can open a terminal and go to there. You're going to create a file, and this is the name of the file we're going to create. It's a rules file. We're going to put these contents into the file. We're going to save the file, and then we are going to run a couple more commands afterwards, and that should fix everything up. So I've got my file manager open to the right place over here. Again, you could open terminal and just navigate to here. It'd be the same thing. I'm going to open up the terminal right now. I will just make the terminal a bit smaller, and we'll just have to jump back and forth so that I can see my my cheat sheet over here. I apologize, it's going to look a little bit odd. Okay, so the first thing we're going to do is we're going to open up the Nano editor. So I'm going to copy this. Let's just make this nice and big so we can see it. I'm going to paste this into it. And it's going to ask for a password because I'm doing a sudo. And I do that, note the password doesn't display. And the nano editor is open, ready to create a new file, which it actually hasn't created yet. This is just a buffer. We have to write it out at the end. Okay, so now let's just bring this up and see what it is I'm putting in the file. And it's this line over here, just one line that goes in my file. So we'll move to the editor, paste that line, make sure we have the whole thing. Do enter, and you'll notice at the bottom there's a Control O to write it out. So that actually writes it to the file. So we'll do a Control O, it confirms the name of the file, we hit enter, it's written out, and Control X connects it. Okay, now we're going to leave the terminal open because we have a couple of commands to run. And so once we've done that, there are two commands. Here's the first one. It looks a little odd when I do that, so I do it this way. And you don't expect anything back, by the way, from either of those commands. And there we go. And you can actually exit out of the terminal right now. And this is the point where we can open up the Arduino IDE and see if it works. And we're back at the Blink sketch right now after making our modifications. Let's see if we can upload it this time. And it looks like it compiles, which it always did. And we got a brief warning, but it did upload. And if you look at the board, you can see that indeed we are blinking the onboard LED. Let's go back up and see what that warning was. Now this is a warning again about the DFU suffix signature, the device firmware update suffix signature. And this is exactly what I get in Microsoft Windows. I get this warning, but then it continues. So by doing the operation we just did with the rules file, we seem to have gotten Linux to the same point. And I really hope that Arduino addresses this in the next edition of the Boards Manager. But now that we can get past this, we can move on and start working with the Arduino GIGA. Now that we've got everything working, we can start working with the Arduino GIGA. And when you install the GIGA board, it installs a number of example files that you can try. So here they are, examples for Arduino GIGA R1. They have camera examples, debug examples. There's all sorts of examples. A lot of these are taken from the Arduino Portenta because it uses the same processor and has similar features. And down over here is one that we're going to try out first, and that's the WiFiWebClient. So let's go and take a look at that sketch right now. Now this is the WiFiWebClient example sketch, and it's actually a pretty simple sketch. It uses the Wi-Fi library, and it's fairly similar to sketches that you've seen using the Wi-Fi library with other processors like the ESP32. Now what the sketch is going to do is it's going to go out and connect to a website. The website they're using is example.com, and example.com is a real bona fide website. It's one that is used as an example. You can use it for code testing. You can also use it within literature if you just want to show what a website is. Now we start by including the Wi-Fi library, and then we need the SSID and password for the network, and we do that by using the second file here, the Arduino secrets file, and we enter our SSID and password into that, and you'll notice we included Arduino secrets over here, so it'll pick that up. Now down over here they show that you can go to example.com and you could place another domain in there if you wanted to. You could try scraping DroneBotWorkshop.com if you like. You can also use an IP address instead, and if you wish, you can put a numeric IP address in here. Now note the format of the IP address. It doesn't use periods in between the different dotted decimal places. It uses commas, so make sure that if you are going to use an IP, you obey that format. Creates a client object, and then just goes through setup. We'll go right to the bottom first because there is a function here called print Wi-Fi status. So it's going to print out things it gets like the SSID, the IP address, the signal strength. Again, you've seen this before if you've used the Wi-Fi library. So we're back up here in the setup. In setup, we start a serial monitor because that's where we're going to display the output. We'll do the usual checking for the module. We'll see if we're connected. We'll connect with our SSID and password. And if we're connected to Wi-Fi, we'll call that print Wi-Fi status that we just looked at so that we can display display some things on the screen. And we'll print some more stuff on the screen, the beginning of the HTTP page. And then in the loop, we go and print the rest of it over here. So we just basically read everything from the client and write it out to the serial monitor, and that's going to be the raw HTML. So let's load this up to our Arduino Giga and watch it in action. Okay, it's all loaded up to the Giga, and I've got my serial monitor open. Now, I'm going to reset the Giga because everything went by so quickly. I want to show you how it all works. So you're going to see it disconnect and connect briefly. So I hit the reset, and there we go. We're unconnected. Now we're connected and attempting to connect to my network, my Wi-Fi network. And there we go, there's the results, and I'll scroll up so you can see them because, as I said, they go by pretty quickly. So we connected to Wi-Fi, we printed that out, as you remember, in the setup, and then we called that function that displays the status of the Wi-Fi, and we display the SSID, the IP address, it's the IP address I've been assigned, and the signal strength, which is very good, but that's not a surprise because there's a repeater for the Wi-Fi right here in the workshop. And then the rest of the setup was started connection to server. We print all this stuff over here. And then the rest of this is what we're actually scraping off of the web page. So you can take a look and you can see the entire HTML of the example.com domain and everything inside there, some style sheet stuff, the body, the actual text, the rest of the HTML, and it disconnected from the server at the very end. So it does seem to work, and it's one of several examples that come with the Giga when you install the board manager. And you could run through a few more of these examples if you wish and try them out with your Giga. But we're going to move on and do some other things with this board. So now that we have our Arduino Giga up and running, we can start exploring some of the more unique features of it. And the first feature we will explore is the real-time clock with its backup battery. Now, in order to hook up the backup battery, you're actually going to need to attach a connector to your board. So get out your soldering iron, I'll show you what it is we need to do, and we can look at some code for using the real-time clock in the Arduino Giga. Before we move on to the code for the real-time clock, I wanted to show you a slight modification that I've made to my Arduino Giga, and it's really not much of a modification at all. It's just over here. I've soldered a 3-pin male DuPont connector here, and that'll be used to connect the battery for the real-time clock. It's also got another pin that can be used as an external on-off switch for the Giga. Now, for a battery, I've got a couple of AA batteries, and this is a real overkill. What you really need is a coin cell, but I don't have any coin cell battery holders. I have plenty of coin cells, but none of the holders. So I just put this together. Most of the coin cells I have are 3 volts, and the Arduino documentation actually didn't specify the voltage, so I assumed 3 volts would be good. Now, of course, the AAs are a complete overkill. It could probably power the clock for 5 or 10 years, and the coin cell would be a better choice, but it's a good choice for our experiments over here. So I'm just going to attach that to the real-time clock, and the RTC battery is on the very end over here, and the ground in the center. And so now that we're connected, we can start doing some experiments with the real-time clock in the Arduino Giga. Now here's some code that we're going to be using with the real-time clock, and this was an example provided by Arduino on their website with some of the Giga documentation, and it worked as advertised. It starts off by including a couple of libraries for the time itself. We define a constant expression, a print interval of 1000 that's going to be used as a time value for our print process, and also we define a function called print now over here. Now we're going to skip the setup and loop for a moment and look at this RTC set function, because this is really what's happening over here. We create a time object called t, and then we define the parameters for t, and so we have the seconds, minutes, hours, the day, the month, and the year over here, and the year is expressed as the number of years since 1900. So this one is preset to 2022, the 11th month, November, the 18th day, so the 18th of November at 14:52 minutes, so 14:52 is the time that we're setting on the 11th of November. Now, of course, this is just a fixed time. This is just a demonstration. You would normally have a method of gathering the time settings and then applying them to this structured object over here. At the end of it, it just does a set time and it passes the structured object to it, and so it sets up the time. And this get local time is a function that's just been defined in order to print the time out to the serial monitor. And so the setup and loop become pretty simple. In the setup, we set up the serial monitor and then call that RTC set to set the time. And then in the loop, we just check to see if the milliseconds has elapsed more than print now. And if it has, we'll go and we'll print what's on the system clock. And then we go back and wait another 1,000 milliseconds and do it over and over again. So let's go and load this up to the Arduino. And there we go. And now we can go into our serial monitor over here, and we'll see that we've got the clock, and it is, as you expected, set to the time. And there's pretty well no surprises over here. Now I'm going to reset the Arduino, and you'll see the serial monitor goes away for a while. And then the time, if you'll notice down here at the bottom of the serial monitor, got reset again to the beginning of the time. So it pretty well does what you expected. Every time that you reset this, it is going to start at that time. I can even pull the plug from the Arduino GIGA, and we'll just basically delete what's in here right now, plug it back in, and it's going to start off again at its preset time. So of course that's not too useful, because every time that we start it, it's going to go to the same time. So what we're going to do right now is do a little modification to this sketch. Now we've already loaded the clock up with our preset time. Let's go and just remark this out and then load the sketch up again. So this is the exact same sketch, except this time in the setup we're not going to go back and set the time. And it's done uploading. Pop over to our serial monitor. Let's just clear the serial monitor. And you'll notice the time over here, it's still incrementing. It didn't go back to the original time. And so we've got our sketch doing this right now. Now, if I disconnect the Arduino from its power source, we can see what's happened. Now, of course, we got nothing going on the serial monitor. Let's just remember the bottom time was 14:52:51. We'll clear that, and I'll plug it back in over here. And 14:53:07, it kept the time, and of course the reason it kept the time was because of the battery backup. And in order to prove that out, let's just remove the battery backup for a second here. And again, I'll unplug it so there's no source of power right now. And remember, we've got a sketch that doesn't set the time when it starts off. I'll plug it back in. And the system clock has gone to 1970:01:01. And for those of you who are familiar with the Unix time format, that is basically the beginning of time according to Unix. What a real time clock does is it counts the number of seconds elapsed since that date. So this does seem to work. The battery backup does indeed hold the time. It won't hold it without it. And as you can see, the real time clock is a fairly simple thing to work with the new Arduino GIGA. Now, another method that you can use to set the time on the real-time clock is to go out to the internet and grab the time from a network time protocol server. And then, of course, you would have a very accurate time setting. Now, this is a pretty common function, and the sketch that Arduino has provided for this, which I've repeated over here, is actually just a repeat of a sketch that's been around for quite some time. You can see some of these dates down over here are about a decade since it was originally created, because this is a pretty standard process. The sketch starts off by including a few libraries, and this is the only area that I had to modify from the Arduino code. They had included the Arduino secrets, but they hadn't set it up over here to look at secret SSID and secret path, so I did that and included the second file over here, as we did with the earlier sketch, that contains both my SSID and password. We open up a UDP port to get network time protocol. We're going to pool.ntp.org, and this will give us back a local time server based upon our location so that we get a very accurate signal. If you want to, you could change this line over here and use the IP address for the time server, and that'll save you a little bit of time because it won't have to go out to a DNS and resolve this, but we're just going to keep it back at this. Otherwise, it sets up a few more parameters. We go into the setup, and in the setup we set up our serial monitor, we connect to the Wi-Fi, we wait for a connection, we wait quite some time for connection, 10 seconds to make sure we have one, and then print connected to Wi-Fi, so we can expect a bit of a delay when we boot this up. And then we call print Wi-Fi status. This is the exact same function down at the bottom over here that we saw earlier, and then we'll go back up to the setup, and then after that we do set NTP time. Set NTP time is a function down here that opens up the port and itself calls two different functions, send NTP packet and parse NTP packet, and these functions are defined below, and basically what they do is send NTP packet, sends the packet out in the correct format to the time server, it waits a second, and then parses the one that's back so that it's a printable thing. And so in the loop we basically do the same thing as we did before. We just wait a second and we continually print the system clock, which has now been updated through the NTP time server. So let's load this up to our Arduino Giga and take a look at it in action on the serial monitor. So we're looking at the serial monitor, and in order to show it to you from the start, I have disconnected the Arduino, so I am going to plug it back in and it should connect. It says it's attempting to connect to my network. Now remember, there's a 10-second delay at the beginning over here, plus it has to go out and resolve the DNS and make its first call to the time server, so we'd expect a bit of a delay, but it should start printing very soon. There we go, it's connected, and it's giving me the system time, and that is the correct time. That's the correct time in UTC, actually. It's 4 hours off my current time as I'm on daylight savings time, but as you can see, it's a pretty solid sketch, and it's a great way to set the clock on the Arduino Giga. Now, in my opinion, one of the most amazing features of the Arduino Giga is the USB-A port. This is the port that would allow you to connect an external keyboard or mouse or USB storage device and use it within your Arduino sketches, and that opens up a lot of possibilities. We're going to work with the port right now, and I'm going to use it with a USB thumb drive. Now, before we begin, though, you need to have your USB storage device formatted correctly. It has to be in FAT32 format. It cannot be exFAT or NTFS, and so you'll need to format the device first. You might have a problem formatting larger devices with FAT32, but there are utilities that will allow you to do that. We've talked about some of these utilities when we worked with the Raspberry Pi and had a similar concern. So get a drive formatted up with FAT32, throw some files onto it, and we can begin working with external USB storage devices on the Arduino Giga. Now for the next few experiments, you're going to require a USB storage device, and I've got a thumb drive that I have formatted with the FAT32 file system, and that's very important. It needs to be a FAT32 formatted device. This is the contents of my USB drive, which I have named USB. Now that doesn't sound very creative, but the reason I named it USB is because the examples that Arduino provided assumed that your storage device would be named USB. So it just makes things a lot simpler. And as you can see, I've got a few files on the drive right now. I just wanted to show you that. There's a text file called arduino.txt, and then there are 5 different wave files, and these are audio samples that I was playing with when I was playing with the digital to analog converters on the board. And we're not using these files at the moment, but I just wanted to let you know that they are on the directory because that'll be relevant for our first experiment, which we are going to do right now. Now the first USB port example we're going to use will be to list all of the files that are on the USB drive attached to the port, which is why I just showed you the directory of them. Now this is some code which was provided by Arduino, and it did work once I corrected a kind of a very funny error in it. You'll need to include a library, and the library is called Arduino_USB host embed 5. Now the problem is if you go go to the demo on the Arduino site, at least if you go to it today, they'll probably correct this eventually, it'll only say USB host embed 5. There's no Arduino prefixing it. And what happened is they actually changed the name of this library in midstream. When I first got my Giga board and experimented with this, it was called USB host embed 5. But then when they released the next version, they changed the name of it. And that sort of threw a loop for me, I'll tell you. But at any rate, this is the correct name of the library, and this is also the library you'll need to install with your library manager. And then after that, we'll just go through the code. Now it's going to go to the FAT file system of a drive called USB. So if you didn't heed my warning about naming your drive USB, you'll have to edit that. And unfortunately, they wrote, let's not do that. And unfortunately, they wrote this code so that this was printed a few times in the code. They didn't make it a variable, so it's really just a basic demo. At any rate, everything is done in the setup. We'll set up the serial monitor, and then we enable the USB-A port. And the way we do that is to hold line PA15 high. So set it up as an output and hold it high, and that enables the port. So it's a very important thing to do. And then while we have the serial port open, we print starting the USB Duralist example. We'll do a connection onto it, and then we'll mount the USB device over here. So assuming we get through here, we've mounted the device, we print down done, and then we display the root directory. And so the rest of this just basically navigates and explains the root directory. Again, if you haven't called it USB, you're going to need to change this over here. So just name your drive USB. It makes it a lot easier. We'll print out the root directory, and then we will close the root directory, and that's all done in the serial port. There's nothing done in the loop. So let's load this up to the Arduino, plug in our USB drive, plug the Arduino back in, and see what happens. And so I have my Arduino Giga ready to go with a FAT32 formatted USB stick in, the contents of which I just showed you. And I'm going to plug in the USB. And if we look at the serial monitor, we get it. It mounts the USB device, it opens the directory, and you can see all of the names of the files that I showed you on my directory. So this works, and it allows us to read the contents of the directory of a USB device using our code on the Arduino Giga. So for our next demo, we're going to use another code sample from Arduino, and this one shows you how you can write a file to the USB drive. Once again, the same caveat about the library. You'll need to install this library with its new name, and we're using a drive called USB. So it starts off very similar as the other sketch did. Again, we're doing pretty well everything in the setup. We are going to enable the USB-A port by doing this, so you remember you always have to do that if you're using the USB port. Same setup essentially at the beginning. We'll mount the USB device, and then we will go and we will write to it. We're going to open a file called numbers.txt. So that's the file that we're going to create. And again, the USB drive name is unfortunately buried in here, so just name your drive USB. And here's the actual command that does it. It's an fopen command. We pass the name of the file we're opening, which in this case is numbers.txt, and the W plus means that we are writing it and we are appending to it if the file already exists. And then we're going to just go through a for loop and count from 0 to 10, and we will print those numbers out to the file, and then after that we'll close the file, and that's the whole program. So really very simple. It's going to create a file called numbers.txt and print out some numbers in that file. So let's load it up and watch it work. And once again, I've loaded the code up to my Arduino Giga, but I have it unplugged now so we can do the demo. My USB stick is in here, and so we will just plug this into the USB-C. There we go. And as you can see, it's on the serial monitor says that it has written the number of numbers out to it, and it's file closed, file closing. And so it looks like it worked. Let's go and pull this USB stick out and make sure it actually did write a file. And here's the directory of my USB stick, and you'll notice I have a new file called numbers.txt, and if I take a look at it in the text editor, it is indeed the numbers 0 through 9. So the code appeared to work quite well, and that can be a very handy thing, being able to write to a text file on the USB stick. You could use it to build some form of a data logger or a number of other different projects with your Arduino GIGA. And the final file example that we have is, of course, reading a file from the USB stick. And this, once again, was code that was provided by Arduino, and it requires that library, the Arduino _ USB host embed 5. And so you'll need to have that installed if you ran the last two programs you already do. Again, we're going to a USB drive that we've named USB, so make your life easier, name your drive USB, or you'll have to change this reference throughout the code. The code is very similar to the write code. In fact, if you go down to it, there really only is one big difference, and it's down over here. When we do a file open, we're opening a file, in this case the one called arduino.txt that's already on there, and we're going to do a read instead of a write, and that's the big difference over here, is we're doing a read. Otherwise, we're going to close the file and exit, and nothing is being done in the loop. It's all done in the setup. And so I've loaded this already up to my GIGA, and so I'm going to open up my serial monitor, and I'm going to reset the GIGA, and we'll wait a second while it resets, and it should run. And there we go. We're starting the USB read file example. Mounts the device, it opens the file, and here's the content of the file. It says, "Welcome to the workshop," and indeed that was the contents of the text file arduino.txt, and then we close the file. So as you've seen from this and the previous two examples, we can list files on a USB drive, we can read them, and we can write to them, and that's going to add a lot of versatility into the programs that you create for your new Arduino GIGA. Now, the next feature of the Arduino GIGA that we're going to examine is the analog to digital converters. Now, I know that's not unique to the GIGA. Pretty well every microcontroller has analog to digital converters, but these A to D converters are 16-bit high-speed converters. They're audio quality analog to digital converters, and when you use these in your code, you use it a bit differently than you would with standard A to D converters. Now, this is one of the few experiments we're doing today that's going to require an external component, just a potentiometer, and that's just so we can get an analog voltage that we can vary and experiment with. So let me show you how we hook up the pot, and then I'll show you how we can code for the 16-bit A to D converters in the Arduino GIGA. Our experiment doesn't require very many parts. In fact, all you're going to need is the Arduino GIGA and a potentiometer. I'd recommend a linear pot of at least 10K or higher. We'll begin by connecting the 3.3 volt output of the Arduino to one side of the potentiometer. Make certain that you are plugged into the 3.3 volt and not the 5 volt output, which is right next to it. You will damage the A to D converters if you use the 5 volt output. There are two pins marked ground, and either one of them can be connected to the other end of the potentiometer. And the analog A0 pin will be connected to the wiper of the pot. And that's it, that's the wiring. Now let's go and take a look at some code we can use with the 16-bit analog to digital converters in the Arduino GIGA. Now here's a sketch that we're going to be using with our analog to digital converters. Now generally when we use analog to digital converters, you would expect that we would do an analog read. And while analog read will indeed work, there is a better solution for these 16-bit high performance converters, and that is to use the Arduino Advanced Analog Library. Now you're going to need to install that library, so you can install that from your library manager. After that, I've defined a pin for the analog to digital converter and created an object that we call ADC1 for the pin, which might be a bit confusing because we're actually using ADC0 over here, but just let's call it ADC1 for the object. We also have a variable that holds the value of the last millisecond reading, and that's going to be because we're going to take the data, put it into a buffer, and read it out every millisecond. Okay, now in setup, we'll start the serial monitor, and here's where we set up the ADC. And as you can see, you can provide it with a number of parameters, including the resolution of it. In our case, we're going to do 16 bits, the number of samples per channel, the queue depth, etc. And if it fails to start, we'll print out over here. Otherwise, if the ADC is started, we end off the setup. Now there's a function called ADC print buff over here, and this is where we take the data and put it into a buffer and then print it out. So we take a look to see if the ADC, the analog to digital converter, is available. We do a sample buffer, and that's a data type, and we call ours buff, that's the name of our buffer, and we will read the ADC. So this is the equivalent of the analog read over here, the ADC read. And then we'll print the contents of that buffer and then release the buffer. So every time we call that, we will print out what's inside the buffer. And in the loop, we're just basically going to call that every millisecond. So we do kind of a loop over here in which we make sure we've had at least a millisecond elapse between readings, and we print those out to the serial monitor. And so it's a fairly simple sketch. As I said, it's different than using analog read, but it has definite performance advantages with this 16-bit analog to digital converter. Let's load it up and take a look at it working. Alright, so I've got my demonstration hooked up, and you can see the serial monitor right now. Now let me move the pot to one extreme, and that's the lower end, and so we're getting a 0. And I'll move it all the way up to the other extreme. And 65,535, that's the maximum value you're going to get for 16 bits. So as you can see, you get an incredible resolution with a 16-bit analog to digital converter. And of course, if you really need analog precision, this is the type of thing to do. Now, one thing I'll warn you about using 16 bits, though, is the inputs are very, very sensitive, so they're susceptible to noise, etc. So if you don't need that resolution, you should cut down the resolution. But if you do need it, or if you want to start working with audio work, then using the advanced analog library and the A to D converter on the Arduino GIGA is the way to go. Now the final experiment that we're going to do today with the Arduino GIGA is to use its 12-bit DAC, and we're going to use some code that Arduino provided to create a waveform generator. Now this waveform generator can generate square waves, sine waves, triangle waves, and sawtooth waves, and you can also vary the frequency of the waveform, and you control everything through the serial monitor using your keyboard. So it's a fun experiment, and it actually could be used as something practical if you wanted to modify it. Now, in order to view these waveforms, you're going to need to connect an oscilloscope up to the output of your digital to analog converter. So let me show you how you do that, and then I'll show you the code that we can use to make waveforms with the Arduino GIGA. Now for this experiment, you will of course require the Arduino GIGA, and you're going to need an oscilloscope so we can view the output waveforms that we're creating with our code. Connect the probe to the scope, and then connect the ground of the probe to one of the Arduino ground connections. Connect the input of the scope probe to the DAC 0 output on the Arduino GIGA. And that's all there is to it. Now let's go and take a look at some code we can use to generate some waveforms using the digital to analog converter in the Arduino GIGA. Now the code that we're going to use has been provided by Arduino in their example codes, and the code itself is actually perfect. It only has one error in it, and the error is right over here in the description. It says on input on A12 or DAC1. Well, A12 is actually DAC0, not DAC1, but other than that, it's fine. So we're really going to DAC0, so everywhere where they reference DAC1, it's really DAC0. Now, once again, we need the Arduino Advanced Analog Library for this. If you didn't do the previous experiment with the analog to digital converter, then you'll need to download that. And we define a couple of constants, the number of samples that are going to be in every waveform, that's 256, and the default frequency, which will be 16 kilohertz. Now we set up our DAC over here by creating an object which we're calling DAC1. It's really the 0 DAC on analog A12, which is also DAC0. We set up a sample buffer with a certain number of samples, and this is an array over here. And we set the DAC frequency itself to the default frequency. Now this generate waveform function is actually the one that takes in the input from the keyboard. In this code, what we are going to do is provide a menu, and the keyboard will be used to tell us what type of a waveform we want, and also to raise or lower the frequency. So we look, and if we get a letter T back, then we'll do a triangle wave, a Q will do a square wave, etc., etc. So for each one of these cases, what we do is we first of all print out the type of waveform we're going to do, and then we go and we fill up that array that we've had. So we do this for loop to the number of samples, which in this case is 256, and we'll go and do a formula here which will create a triangle, and we'll fill up the sample buffer with the triangle. Remember, the sample buffer contains one complete waveform. And for the square wave, we do the same type of thing, but it's a different formula. Same for a sine wave down over here, and for a sawtooth wave. Now, if we want to raise or lower the frequency, we use the plus or minus keys, and if we see that in the case statement, then we take a look, make sure we haven't exceeded 64 kilohertz or gone below 1 kilohertz, and we either multiply the frequency by 2 if it's a plus, or divide it by 2 if it's a minus. And the final function in the case statement, is a DAC stop, which will stop the DAC after the end of the waveform. And over here, this is the default, is an unknown command if you happen to press a letter in the keyboard that doesn't mean anything. After that, we'll print out the DAC frequency, and we divide it by 1,000 so we can display it in kilohertz. Now in the setup, we set up the serial monitor, and we print out all of our commands so we can see them on the screen, and then we call generate waveform, which is the one that we just showed you over here. Now here's how we initialize the DAC. So this is the line that shows you how the DAC is initialized, and we can initialize the resolution, the default frequencies, the number of samples, etc. And then in the loop, we just basically go and see if the serial port has brought us a command, and if it has brought us a command, we call generate waveform. And if the DAC is available, we'll fill up a buffer. This is the same type of thing you saw in the analog to digital converter. We're going to use a buffer. We will fill it up. We'll write the data to the buffer, and then we'll write the buffer out. So the data in the buffer is going to be one waveform of the DAC sample. So that's the code we're going to use. Let's upload it, hook up the scope, and make sure that we are actually generating waveforms in response to our keypad presses. So I've got the Arduino hooked up to the scope right now, and I've just booted it up, and if you take a look at the serial monitor, you can see I'm being asked to enter a command, and it's giving me a number of commands I can enter with the keyboard to create a different type of a waveform, and it's telling me at the bottom that I have a sine wave of 16 kilohertz being output right now. And if you look at the oscilloscope, we can confirm that there's a sine wave, and if you can see the frequency reading at the bottom of the scope, it is around 16 kilohertz. So right now, let's give it another command. I have a T here, I can give it for a triangle. Let's do that. And as you can see, we seem to have a triangle wave right now, same frequency. Square wave is a Q, so we'll do a Q, and there's our square wave. A sawtooth wave is an R, and there's our sawtooth wave. That's pretty cool. And we can go back to doing a sine wave with an S again. Now we can increase or decrease the frequency, and if you remember the code, this will either double or half the frequency. So let's give it a minus sign over here, and we'll enter that, and it tells it that the frequency is 8 kilohertz. And if you look at the scope, the frequency has indeed dropped down to 8 kilohertz. And if I were to give it a plus instead, it'll bring the frequency back to 16. I can give it a plus again. And we now have a 32 kilohertz wave going. So this is a pretty cool little project. It's obviously something you can build upon to make an even more functional waveform generator, but it's a great demonstration of the accuracy of the 12-bit digital to analog converters in the Arduino GIGA. Now, one feature of the Arduino Giga that I was not able to demonstrate to you today was the camera connection, and it wasn't for lack of trying. I bought a number of cameras from ArduCam that can be used with this board, and I followed the examples that Arduino provided, but I cannot get it to work, even though this particular camera here is the actual camera they use in their example, and I've got two of them, so I know I don't have any bad hardware here. I suspect the reason I can't get it to work is the fact that the library that I use is currently at version 0.002, and it's probably an alpha copy of something that was taken from the Portenta and still needs some work to work with the Arduino Giga. And you're going to find that with a lot of the code examples provided for this. But that situation will improve. This is an excellent piece of hardware, and I think it has a lot of great applications. I mentioned robotics earlier, but one application that came to mind when I was using this was to use it in my Water Your Garden with IoT project, where we use the Arduino cloud to control things like moisture sensors and pumps and that. Well, this board would be absolutely perfect for that. With all of those I/O sensors, you could control a farm with this thing, let alone a garden. Now, I'll tell you, this is not an inexpensive board. Although it's about half the price of the Arduino Portenta, it is still an expensive board. To put it in perspective, I could probably pick up about 4 or 5 expressive ESP32 boards for the price of this one board. But of course, it's not a fair comparison. This is much, much more powerful than the ESP32, and it has all these I/O ports and additional features the ESP32 does not have. One feature it doesn't have that kind of surprised me, though, is it doesn't have an I2S connection. And it surprised me because it has these audio quality A to D converters. It has a jack on it for audio. You would think they would look at audio applications, so the lack of I2S was a bit confusing. But otherwise, it has a lot of great features, and I think we can do a lot of great things with the Arduino Giga board. Now, if you want some more information about the board, or if you want to download the sketches I used today, you'll find that on the article that accompanies this video on the DroneBotWorkshop.com website. There's a link to that article right below the video. While you're on the website, if you haven't yet, please sign up for my newsletter. It's not a sales letter. It's just my way of occasionally reaching out to you to let you know what's happening here in the workshop, and of course, it's free to sign up. You could also join the DroneBot Workshop forum, where you can talk with a number of like-minded individuals about your electronic projects and get any help that you might need. And finally, while you're in the subscribing mood, please subscribe to the YouTube channel if you haven't already. I make videos about microcontrollers and robotics, and I'm sure they would interest you. So all you need to do is to hit this little subscribe button that you'll find below the video, and also click on that bell notification. And as long as you've enabled notifications in your web browser, you'll get notified every time I make a new video. So until we meet the next time, please take care of yourself. Please stay safe. Enjoy your Arduino Giga if you have one, and we'll see you again soon here in the DroneBot Workshop. Goodbye for now.